Welcome to Ask and Learn.
We are given a deterministic finite state automaton, and we are asked to show that the language recognized by this machine is infinite if and only if there is a word recognized by the machine which has a length larger than the number of states in the machine. So, first of all, suppose that the language recognized by M is infinite. Well, then it follows that the length of the words recognized by M must be unbounded. After all, there are only a finite number of symbols out of which to make these words. And therefore, it follows that L of x is going to be greater than or equal to the number of set states for some word x. Because the number of states is finite. On the other hand, let x be a word recognized by the machine such that the length of x is greater than or equal to the number of states in the machine. And now let S0, Si1 all the way up through Sin be the sequence of states the machine goes through on input of x, where n is going to be equal to the length of the string x. Of course, as long as x is a word of finite length. And we have that Sin must be a final state. Now, we see that by the pigeonhole principle, some state occurs twice in this sequence. This is because the number of states in the sequence is going to be the length of x plus 1, which we know is strictly greater than the number of states in the machine. And therefore, there's a loop from this state back to itself during the computation. Now we'll let y be the substring of x. Essentially, y is going to be substring that causes the loop. In other words, we have that x is equal to u, y, v for some other words u and v. And it follows that for every non-negative integer k, the string u, y to the k, v will be accepted by the machine M. Since the computation is going to be the same as the one on input x, except the loop is going to be traversed k times. Now, since there are an infinite number of non-negative integers, it follows that the number of words recognized by this machine is infinite.